discussing the rectangular wear and the various equations that you have already studied in your fluid mechanics 1 course. Now the next thing, that is the rectangular wear with end contractions. What we mean by end contractions? You see here this figure which is given in your textbook chapter 11. So in this case you see that when the length of the wear, it is less than the length of the channel. Clear? When the length of the crust of the rectangular wear is less than the width of the channel, the nappy will have end contractions so that its width is less than L. What we see here is that you see here, this is the nappy. Yes, what is the question? Yes, what is the question? Now this is the length, so you can see that the length of the nappy is less than the L, which is the length of the wear here. You can see here, this is now the length of the wear. So now in this case, you see that the width of the nappy, that will be less than L. So in other words, we have this contraction. How much is the contraction? Normally, when we have this as the top view of the channel, when this, where it occupies the total length here, this is now the total length. So you see there the water will flow. There will be no contraction. There will be no contraction here. There will be no contraction. But when we have the length of the wear which is less than, let's say here, so you see that the water, it will flow and it passes, there will be a contraction before it moves in the channel. Clear? When it comes here, so there will be a contraction here, just like you studied in orifices. Clear? And then it will continue to flow. So this we mean by end contraction. And this end contraction is h by 10. This has been found experimentally. Experimentally, it has been found that this contraction is 0.1 times h. This is 0.1 times h, or h by 10. Now in this case you can see that there are end contractions on both sides. It can be on one side also, depends on the design of the wear. So for this, then what will happen is that the effect of end contraction is to reduce the effective width of the nappy, because it reduced the effective width of the nappy by this 0.1 times h, and then from both sides. So that's why the equation that earlier we write down, this equation is then equal to Q is then equal to CW into L minus 0.1 N. N is the number of end contractions, into H, into H3 by 2, into H3 by 2. This is then the equation. Now in this case, this N is the number of end contractions. This N, small n, this is equal to number of end contractions. Now in this figure, this contraction is on both sides, so N is equal to 2. But N can be 1. For example, if there is only contraction on one side, this depends on the design of the wear. Clear? Number of end contractions. So that's why this equation, this we can write down is Q is equal to 3.32 into L minus 0.1 times N into H into H3 by 2. This is in BG units. And also this is equal to 1.83 L minus 0.1 N into H3 by 2 in SI units. So these are the formulas that we can use, and these formulas are known as Francis formula. These are known as Francis formula. Now you can see that we have this rectangular weir with end contractions. So if we do not have these end contractions, then in that case it will flow full. This will be the shape of the nappy. You see here, it will flow full. It will not be contracted. It will flow full. So then in that case, n will be 0, and this n is equal to 0. Then it reduces to the formula. And in here, because in that case, the end contraction that will be suppressed means no end contraction. When we do not have end contraction, it means the end contractions are suppressed. So that's why in this case we call it as suppressed rectangular weir. It means that the end conditions, they are suppressed. Clear? Now this end contractions that we have, so one way is you use this formula. One way is that you use these formulas that we have written here. Another way is, if we want to avoid this end contraction effect, we want to offset this end contraction. In order to avoid correction for end contraction, then we have another criteria, what is known as Cipollati weir. So it is a trapezoidal shape. It has a trapezoidal shape with side slopes of 4 vertical to 1 horizontal. This is an example of Cipollati weir. It has basically a trapezoidal shape where in which this angle here is 1 horizontal to 4 vertical. 1 horizontal to 4 vertical. So this additional area that we provide, because now you make the shape trapezoid, clear? This additional area adds approximately enough to the effective width of the stream to offset the lateral contraction. This lateral contraction that we have, you see here, this lateral contraction that you see here. So if we want to offset this, either you use this formula, you apply for end contraction, or another way is we provide this Cipollati weir, for which it has been determined that if you provide the slope as 4 vertical to 1 horizontal, so this additional area adds approximately enough to the effective width of the stream to offset the lateral contraction. Next we have the V notch or triangular notch, which is suitable. It has the advantage, it can function for a very small flow and also measure reasonably large flows as well. Clear? So this is the vertex angle here, theta, which you can see. This is called the vertex angle. If we have very small discharges, you might have studied the advantages of triangular notches and wears that it can accurately measure as compared to the rectangular notch or wear. So in this case, you already developed this equation. Q is equal to CD 8 by 15, CD 8 by 15 into square root of 2G into tan theta by 2 into H5 by 2 into H5 by 2. So this theta, this is the vertex angle, which you can see here in the figure. This is the vertex angle. And it is usually between 10 to 90 degree. This is between 10 to 90 degree. Clear? Now you already developed this formula in your fluid mechanics 1 course. So there is a graph available in your textbook in chapter 11. So that graph is this one here. These are the coefficients for V notch wears. Clear? These are the coefficients for V notch wears. These are obtained by 3 different experimenters. You can see here this graph is actually obtained by 3 different experimenters. So that's why you see the solid lines and you see the dash lines. And also you can see that this CD, this is equal to 0.581. This is the minimum value for all angles. This is the minimum value for all angles. Clear? Now in this case you see that this is the coefficient of discharge. This is for the triangular notch and this is the formula. Now you can see that this is the head. So when the head decreases, let's say for example we come here and we take this 0.5, and if I draw a line here, so you can see that this is shown here for theta is equal to 10 to 90 degree. This is what we write down here, that it varies 10 to 90 degree. So now in this case you see from 10 theta is equal to 10 to 90 degree. If I consider this head, so 0.5, when this is 0.5 feet, you see here there is a increase. There is an increase in the coefficient of discharge. You can see here increase in the coefficient of discharge, solid lines. So the rise or increase in CD at heads less than 0.5 feet is due to incomplete contraction. The reason behind this is that this is due to, because this is coming from experiments. So this is due to incomplete contractions. At lower heads, the frictional effect reduce the coefficient. You can see here, if we come to these figures here, you can see that at low heads, so there is a decreasing. It means there the CD is decreasing. So at lower heads, the frictional effects reduce the coefficient. And at very low heads, when the nappy clinges to the wear plate, you see, let's say this is the wear. Let's say this is the wear, and now the water flows over the wear. So it is like a free stream, clear? And then the water joins the downstream and it flows. So this is a free nappy. But if we have very low discharges, very low head, what will happen? That instead of a free nappy, what will happen is that it will clinch to the plate. Like it will flow like this. In the channel, it will flow like this. It will clinch. This we call it as clinch. Clear? It will clinch. So when the nappy clinches to the wear plate, then we cannot say it is a wear flow. So we cannot use the equations to calculate the discharge. Clear? So this already you have studied. I'm very brief on this. Now my main focus will be this broad crusted wear. This is what we are going to discuss in detail. just like you did the practicals on the notches, rectangular notch and triangular notch in your fluid mechanics 2 course. Similarly, we can conduct an experiment on broad crusted wear also, clear, in order to estimate how to calculate the discharge. Before we do that, so in case of the broad crusted wear, broad crusted wear provides a stretch of elevated channel floor over which the critical flow takes place. Now we are coming to that basic idea that we have to establish the critical depth in order to accurately measure the discharge, clear? So you can see here the sill or crust of the wear that is broad. So that when the water flows, the critical depth is established. And we are interested in the critical depth. Why? So that we can measure the discharge accurately. As we already discussed, talk about the control section. Because the control section provides a definitive stage discharge relationship. So we can accurately estimate the discharge. So that's why the idea here is that this broad crusted wear provides a stretch of elevated channel floor over which the critical flow takes place. So this is the main idea or principle behind the working of the broad crusted rectangular wear. Clear? So let us see how we develop the equations that can help us to calculate the discharge. Now this is the broad crusted wear which I explained to you. You can see here that this is the flow which takes place over the broad crusted wear. So the height of the wear is such that this critical depth, it will form over the wear. This is how we can then use it as a measuring device. So this critical depth which we talked about earlier, which will occur here as the water flows in here. So you can see that in this critical depth, the water will flow down, and immediately downstream we have the supercritical depth here, and then it will be followed by a hydraulic jump to dissipate the energy, and then the water will flow with the normal depth in the channel. So the main idea behind this critical depth is that we can measure accurately the discharge. So you can see here, this is the broad crusted wear. The water flows here. You can see the depth is subcritical here, the flow. I will discuss if we have supercritical flow, then what will happen. And the idea here is that the critical depth will form over the crust of the wear. So over the crust of the wear, the critical depth will occur, YC. That what you can see here in this diagram. You see this is the height of the wear, this is P, this is the head of water, and because the water is approaching the wear with a velocity v naught, this is known as the velocity of approach. So that's why v naught square by 2g. In most of the problems you might have studied in fluid mechanics 1, it may be mentioned you neglect the velocity of approach. But if we consider the velocity of approach, then we have to consider this velocity head also along with this h. And as the water flows over this wear, this is the broad crusted wear, you can see that the critical depth establishes. And that's why we can calculate accurately the discharge. So this is the main principle behind the broad crusted wear, is that the critical depth establishes as the water flows over its crust or sill, and from there we can develop the equation to calculate the discharge. Clear? So let us first develop the discharge. So what we are saying is that for rectangular channel, as we already discussed, for rectangular channel, what we have is that we see the critical velocity that is equal to under root gyc. This is square root of gyc. This is the critical velocity, and we already studied that the critical depth is equal to 2 by 3 times the specific energy E. This is equal to 2 by 3 times E. This is the critical depth. Now for broad crusted wear, this is for a rectangular channel. So for the broad crusted wear, what we can write down is that Q is equal to AV. This is the basic equation. Q is equal to A times the flow area multiplied by the velocity. So now in the case of broad crusted wear, what will be the flow area? Because the critical depth establishes, so it will be length of the wear multiplied by the critical depth. Clear? So this will be further equal to, and this is the area. Clear? So we have to multiply with the velocity. So in here, what is the velocity? Under root gyc. This is the velocity. So L into yc is the area, and then this is equal to g, acceleration due to gravity, into yc. And this can be further equal to L into under root g into yc 3 by 2. So you can use now, you see, and calculate the discharge. You can use this one, you can use this one, and now you see if you can measure the critical depth, so you can easily calculate the discharge. And this will also be equal to, because yc is equal to 2/3 of E, so this can also be equal to, this can be further equal to L into square root of G into 2 by 3 this is power 3 by 2, this is power 3 by 2 into E power 3 by 2. This can also be written L into square root of G into 2 by 3 power 3 by 2 into E 3 by 2. Anyone you can use, you see, you can calculate the discharge. Now this E which is written here, this E is actually equal to what? H plus V naught square by 2G. This is equal to H plus V naught square by 2G. So this is the measured head, and this is the approach velocity. V naught is the approach velocity. Now let's say this is equation number A. This is equation number A. And we already studied this equation, that Q is equal to CD into 2 by 3 for the rectangular notch. We also studied this equation, CD 2 by 3 under root 2G into L into H 3 by 2. Now if you put equation B in equation A, clear, put equation B in equation A, which is, this equation is applicable to broad crusted wear as well as sharp crusted suppressed rectangular wears. So what we will get is that from this equation B and A, you will get that CD. From there you will get this CD is equal to, or let me write down complete so that you know how it comes. CD into 2 by 3 into under root 2G into L H 3 by 2. This is equal to L into under root 2G. 2 will not be written. This will be equal to L into under root G into 2 by 3. This is power 3 by 2 into E 3 by 2. Now when you simplify this, what we will get is that this CD, this will be equal to 1 divided by square root of 3 into E by H power 3 by 2. Power 3 by 2. Now in this equation, for very high VARs, what will happen if we have very high VARs? So for very high VARs, when the height is more, what will happen? H will be more. For very high VARs, what will happen is that this H by P. Now P is the, what is P? This is P. Now when P is more for very high VARs, what will happen? This H by P, this will be small. This will become small. Because you increase the P, this P will become small. So now when this P becomes small, the velocity of approach becomes small. So V naught, this velocity of approach, it will become small. So when this becomes small, this E, this velocity of approach becomes small, E will approach H. In here you can see that E will approach H. When this becomes small, so what will happen, that E, it will approach H. And when E approaches H, clear? So what will happen? When E approach H, then what will happen? E by H. This E divided by H, which is here, this will approach 1. When E approaches H, so what will happen? This E by H, it will approach 1. And what will be the result of this? That this CD, it will approach 1 divided by square root of 3. This will approach 1 divided by square root of 1 by 3. 0.577. That's why you see that in the problems we are commonly assuming in the problems that consider the coefficient of discharge as equal to 0.6 or 0.577. Clear? So now remember, the actual value of CD for a broad crusted weir depends on the length of the weir and whether or not the upstream corner, that is edge of the weir, is rounded. The actual value of CD for a broad crusted weir will depend on the length of the weir and whether or not the upstream corner of the weir is rounded. Upstream corner, this one, whether this is rounded or not. Clear? So experimentally we determine these values. Now, so far we consider that the flow here is that of subcritical. Clear? So if we have supercritical flow, this is just to finish now this broad crusted wear discussion, you see that we can estimate this uh, discharge, how we calculated for the broad crusted wears. So now in this case, what happen is that if the approach velocity, this is now the wear, and if we have the flow as supercritical, so what will happen, it will try to flow over this. Now what will happen, now the depth is less, clear, and if we have the approaching flow is supercritical, now we say that this flow is supercritical. What will be then the situation? So if we have this as supercritical, you see that it will try to flow over here. So as a result of this, waves will form here. So these waves, surface waves, you see the presence of surface waves causes the broad crusted rectangular waves to be impractical for use as metering devices. Then we cannot use this as for measuring purposes. It is written in your textbook, chapter 11, read it, that the presence of surface waves causes broad crusted rectangular waves to be rather impractical for use as a measuring devices. So when we have supercritical flow, then it is impractical to use it as a measuring device. Clear? Now, before we discuss Venturi flume, I show you one video that how we can uh, do experimentally the broad crusted wear. So you can see here. This is the broad crusted wear. You can see the critical depth is established. This is width of the wear. So this is how we estimate the discharge. So this should be 1.704. So you can see in the video that how we can conduct the experiment, just like we studied in fluid mechanics 2 for rectangular and triangular notches, we can also have a similar experiment for broad crusted wear. Clear? Now the next thing is the Venturi flume. So the Venturi flume, before we discuss how it is used to measure the discharge, so the use of a wear is probably the simplest method for measuring the discharge in open channels, is what we have studied so far. However, there are certain disadvantages. When we use the wear, there are certain disadvantages. What is that? The relatively high energy loss. You can see here that the coefficient, that is 0.577. So it means there is loss of head, loss of energy. Clear? 0.6. So this is one disadvantage, that using wears we have relatively high energy loss, and the sedimentation deposited in the pool immediately upstream of the wear. When we have a channel and we have a wear, as you saw in the video also, the water level will rise, and as the water level rises and then it passes through the wear, over the wear, so what will happen if there are some suspended particles in the flow, that particles will settle down here. So it will cause sedimentation behind the wear. These particles that will settle down. So this is sedimentation. So we have the sedimentation deposited in the pool immediately upstream of the wear. So these are disadvantages of the wears. Clear? Now these difficulties can be partially overcome by using a critical flow flume, which was also known as Venturi flume. This is a critical flow flume, and this was at that time was also known as Venturi flume. The major disadvantage is that a flume installation is typically more expensive than a wear. Although it solved these problems of high energy loss and sedimentation, but one disadvantage of using the flume, that is that it is expensive as compared to the wear. Now a variety of Venturi flumes have been designed for field applications. Remember, there are many types of Venturi flumes. There are many types of Venturi flumes that are developed in different countries, in the US, in Italy, in England, in Argentina, so on. Many countries, they develop very good designs of the Venturi flumes. Clear? But in here, the most extensively used critical flow flume means that the critical depth will occur. The most extensively used critical flow flume in the United States is the partial flume. So this is very commonly extensively used because it was standardized. And why it is called partial flume? Because in the 1920 or somewhere written 22, so it was developed by R.L. Partial. So it was then named as partial flume, and this is extensively used in the US for discharge measurement. Clear? Now this Venturi flume is nothing but it is actually a contraction. You see here that the water flows in this contraction, and we are using this as a measuring device. You can see here different types. So the water flows clear in here, and similarly you can see here that this is just a contraction which is provided in a channel. The water flows in this contraction, and we are using it as a measuring device. Now we will discuss how to calculate the discharge. So you can see that this Venturi flume, it is nothing but it is just a contraction provided in the channel, open channel for flow measurement. So this is the similar, just like you studied the Venturi meter. In the Venturi meter for pipe flow, that we have a convergent cone, then we have the throat section, then we have the divergent section. So the idea is to produce the pressure difference. and then that is used as a measuring device for pipe flows. Clear? Similarly, this is a contraction which is provided in the open channel, and it is so that the critical depth is established, and we can use it as a measuring devices for the discharge. So let us see that how we use it for discharge measurement. Now, our main focus will be that on partial flume. As you saw that it is extensively used in the US. So for flow measurement applications, that's why our main focus will be on partial flume. But remember, there are many designs of the flumes that are developed in different countries. Clear? So this partial flume, you can see that it is a contraction and the water flows. You see here the water will flow in this channel. It passes through this Venturi flume, which is known as the partial flume. This is known as the partial flume here, you can see. And after it passes and the critical depth establishes, you can see there is a free flow and we have this hydraulic jump. You can see here this hydraulic jump forms, and then the water continues to flow in the channel. Now, this was developed by R.L. Partial, so that's why this is known as partial flume. Clear? He actually developed this in the 1920s or 1922 here in Colorado, US. So this, the name partial measuring flume, this was adopted for the device by the executive committee of the irrigation division. We have American Society of Civil Engineers, right? We have American Society of Civil Engineers. They have subcommittees. So the executive committee of the irrigation division of the American Society of Civil Engineers, during their annual meeting in December 1929, during their annual meeting in December 1929, they adopted this name, partial measuring flume. And that's why after that, so they call it as the partial flume. Now let us see that this is actually a 15-foot partial flume in Colorado, USA. You can see here 15 foot. What we mean by 15-foot partial flume, that I will explain. This is the size of the flume. We have different sizes for the flumes. Clear? So this is a 15-foot partial flume. I will show you that what we mean by this size of the partial flume. Now you can see here that this is a partial flume. It has a converging section. So what will happen, that this is the channel, the water comes here. This is a converging section. Then you can see here that this is the throat section, similar to the Venturi meter. We have the throat section, and then after that we have diverging section. We have this divergent section, and then the water continue to flow in the channel. Now in this case, this HA means that the water depth we have to measure at this point in the flume. This one measurement is necessary, as I will show you the formulas, but sometimes we need to measure this depth also in the throat section. In the throat section of the flume, we also need to measure this depth, which is HB. Also there can be HC, but primarily we need this HA, and also we need this HB, because we need it to see that if the hydraulic jump is submerged or not, because it has effect on the discharge. Then that I will explain. Now in this case, you can see that these dimensions here, P, this dimension here, D, this is A, this HA, you have to measure 2/3 of A from here. This W is the width of the throat, and this determines the size of the flume. Clear? Similarly, you can see what should be the slope here, and these dimensions M, B, T, and G. You can study in detail. So this is, you see this figure is from US National Resources Conservation Service. So because as I said, they standardized the partial flume. So that's why in order to use it for discharge measurement, you have to construct the partial flume as per the standards. So the standard is, for example, mentioned here, this table you can find on the internet. So you can see here all the dimension. This is the width of the partial flume W, which you can see here. This is the W. So this is the W here, and all these dimensions, for example, this C, this Z here, this M, B, T, G, that you can see here. This is B, this is A, which I show you, the B here, C here, D, clear, all these dimensions. So it was standardized, clear, because it was adopted as a measuring device. So then it was standardized that you have to construct it as per the standard in order to use it as a measuring device, clear. So since it was standardized, then what happened is that this is another clear picture of this. You can see here the various dimensions. It can vary from literature to literature, clear. For example, this is MB, F and G, but this was standardized that the slope should be how much here, similarly these angles, etc. So it was standardized. When you construct it, you have to follow these standards in order to use the formula and calculate the discharge, clear. So how to calculate the discharge? Because it was standardized, by conducting large experiments on this so that this can be adopted as a measuring device for open channels. So what happened is that from the experiments, empirical discharge equations were developed to corresponding to each flume size. And the flume size is that of the width. You see, this is the width of the throat section, which is denoted by W. This is the size. This determines the size of the flume. This determines the size of the flume, clear. So for various sizes, what happened is that from experiments, discharge equations were developed. What are those equations? These are those equations for British gravitational system. Remember these equations that we discuss here, these are for the British gravitational system. This is for the BG units. You can find literature on the internet that maybe these equations are used for the SI units. Clear? There can be equations that are used for SI units, but these equations shown here, these are used for BG units. These are used for British gravitational system. So now in this case, you can see that the throat width is 3 inch, 6 inch, 9 inch, can be 1 to 8 feet, and can be 10 to 50 feet, up to 50 feet, clear. Q is the discharge, that we measure the discharge. HA is the reading. You see here mostly we have HA. W is the width, so that is known to us. HA is the reading that is involved, and these are the ranges for this free flow capacity in CFS. Remember, in British gravitational system, so this is in CFS. Now what is this HA? HA is this one. You see here, this reading you need to measure. What is the water depth here? When the water passes through the here, this section, so in here, what is the water depth here? This depth you need to measure. This is your HA. This is your HA that you can see in the formulas. So you see that in the formulas, you see HA, HA, HA here, HA, and so on. So it means that in that section here, you need to measure this HA. When you have this HA, what is the depth of water here? Then you can apply according to the size of the flume. You can use these equations to calculate the discharge. And this discharge is for the free flow capacity. This discharge, this is for the free flow capacity. What we mean by the free flow capacity? If I go back, you can see here that after this water, it passes through this here, this convergent section. We have this converging section, then we have the throat section, and then we have the diverging section. After it passes here, you see that this passes through here, and then we have the hydraulic jump, and then it flows with the normal depth in the channel. So this is free flow. This is free flow. Clear? Sometimes what happens is that this hydraulic jump can be submerged. It means that this can be the surface here. You see that this can be the surface here. The surface can here. So in this case, this is the water surface. Here, water depth increases. So in this case, what happens? This is submergence. This is important now. That this hydraulic jump, it can submerge. Clear? This is known as submergence. So in this case, we say that the flow is submerged. So in this case, we have free flow. Remember, these equations that we have developed, these are for free flow capacity. We have free flow. So these equations that are developed, these are for free flow capacity. Now, if it is submerged, you see the hydraulic depth, the jump that is submerged, then what will happen is that the effect will be to reduce the flow. What will happen if this becomes submerged? What will happen? It will try to reduce the flow. So when it tries to reduce the flow, then the discharge calculated by these equations will be greater than the actual discharge. So that's why we have to apply a correction. When we calculate the discharge, we have to apply a correction. Clear? If we have free flow, then just directly use these formulas. Directly apply these formula for the given size of the flume. You directly apply these formula and get the answer. But if we have submerged condition, clear? So then in that case, what will happen is that the discharge that will be occurring will be less. But when you apply these formulas, the discharge will be more. So it means we have to apply a correction. Now the next question is how to calculate, how to know that we have submergence or not. How to know that we have submergence or not. So for this, we have certain limits that we have to see. If that limit is crossed, we will say that it is submerged. The discharge is submerged. And what are those limits? So the limits are that when we have this ratio, you have to calculate. What ratio you have to calculate? This HB. This is HB divided by HA. This ratio you have to calculate. And what is HB? You see, this is HA, which you see in all the equations, and this is HB. This you need to calculate. HB here. This you need to calculate. So when you calculate this HB by HA, if this is more than 0.6, if you calculate and this is more than 0.6 or 60%, clear? And this is for this is for 3 inch. Here written 3 inch, 6 inch and 9 inch. 3 inch, 6 inch, and 9 inch. We will say that we have submergence if this ratio is greater than 0.6. And if we have this ratio, it is greater than 0.7, if this is greater than 0.7, clear, if this is greater than 0.7, so then this is for 1 to 8 feet. This is 1 to 8 feet. These are the limits. These will tell us we have submergence or free flow. And if it is greater than 0.8, if it is greater than 0.8, clear, that is for 10 to 50 feet. That is 10 to 50 feet. So if these limits are greater than 0.6 for 3, 6 and 9 inches, greater than 0.7 for 1 to 8 feet, and greater than 0.8, 10 to 50 feet, so this will indicate that we have submergence. Clear? So flow becomes submerged. It says that flow becomes submerged. And we have to apply correction to these equations. Clear? So how to do it? Let us try to see that in this case, this is the head HA which we measure, and this is the correction in CFS. Remember, this graph is for CFS, British Gravitational System. And these lines, curves that you can see here, so this is percentage of submergence. So when your HB by HA, it is 70%, 72%, 74%, up to 96%. Then we have to calculate the correction. If we have submergence, if we have less than this, no problem. But if we have submergence in this range, then we have to calculate the correction. So this graph is developed for 1 foot submerged partial flume. This graph is developed for 1 foot submerged partial flume. But the same graph can be applicable to other sizes. For example, you see here, for 1 foot size flume, the correction is 1. And you get any value from here, that is the correction, subtract from the discharge that you calculate here. From these equation, 1 foot. So 1 foot is here, this is 1 foot. You calculate the discharge from here and then apply the correction from here and calculate the actual discharge. But the same graph can be applicable for 2 feet size, 3 feet size, 4 feet size, 6 feet size, and 8 feet size flume. Remember, this is not the only graph. The similar graph can be developed for all the sizes. These graphs can be developed for 3-inch size, 6-inch size, 9-inch size, 1 to 8 feet size, 10 to 50 feet size. So this is not just one graph. You can have many similar graphs that can calculate us the correction that need to be applied for the submergence, and we can accurately estimate the discharge. So let us apply these concepts to solve a problem that we understand how we can calculate the discharge. So this graph is for 1 foot, as written here, 1 foot submerged partial flume. If we have, let's say, 3 feet, then in that case, with this correction that you get from the graph, you have to multiply with 2.4. Why? Because this graph is for 1 foot flume size. In order to be applicable for 3 feet size flume, you have to multiply with 2.4 and this correction. Let us try to solve a problem. You will understand that how we apply this correction. Clear? So this is a problem, a sample problem. Now we have a 4 feet partial flume that is installed in an irrigation channel to monitor the rate of flow. The readings at gauges HA and HB are 2.5 foot and 2 foot respectively. Determine the channel discharge. Now the size of the partial flume, that is 4 feet. This is the size of the partial flume, 4 feet. So HA that is given. Now let us try to solve this problem here. So we have HA that is given. HA is equal to how much? 2.5 feet. So this is equal to 2.5 feet. HA is 2.5 feet. Clear? Now, what is the formula for 4 feet? So for 4 feet, this is 1 to 8 feet size. 1 to 8 feet size, this is the formula. So this formula we have to apply. This formula here. So we apply this formula. So Q is equal to 4 times W times HA into 1.522 into W into power 0.026. Remember, this is power of a power, so don't make the mistake here. Clear? 4WHA power 1.522 into W into power 0.026. Don't make a mistake here. You see power of a power. So we calculate the discharge, you put the values, and we calculate the discharge from here. Everything is known. What is W? W is 4. W is 4. Clear? And HA is 2.5 feet, which is given here. So we calculate the discharge, that is 67.92 CFS. This is 67.92 CFS. This is the discharge. But this is the free flow discharge. These formulas, they are developed for free flow. This is the free flow discharge. This is the free flow discharge. Now, if we have free flow, then this is the answer. This is the answer if we have free flow. But we have to check that we have free flow discharge or we have submerged discharge. So how to know? We have to calculate this ratio, HB divided by HA. We have to calculate this ratio, HB by HA. So what is HB? It is given as 2 feet. So this is given as 2 feet and HA is given as 2.5. So if you calculate from here, so this is equal to 80%, 0.8. This is equal to 80%. And what is the limit for 4 feet partial flume? What is the limit? HB by HA for 4 feet is 0.7. So it means that it is greater than the limit. It is greater than 0.7, which is the limit. So that's why the flow becomes submerged. Clear? We have submerged flow. So it means we have to now apply the correction for this. We have submerged flow. We have submerged flow. So how to apply the correction? So now we have to come to this graph here. Now in this graph, we have this HA. And what is HA with us in the problem? It is 2.5 feet. This is HA, 2.5 feet. So this is HA, where is 2.5 feet? Here, this is 2.5 feet. This is 2.5 feet. Clear? So now we have this HA. This is 2.5 feet. And now you come here. Now in this percentage of submergence, HB by HA, percentage of submergence, how much is percentage of submergence in our case? 80%. This is 80% submergence, 80%. So now we come here, locate the 80% here. So we have this 2.5. Now you have to move here, and 80% is here. This is 80%. This is 80% of submergence. So you move along this curve here, and it is here, this point. So this is 2.5. You come here, this is 2.5, and this is 80%. This is 80%. And then you go vertically here. So this value you need to read. This value, if you read, this is approximately 1.8. This is the correction. So it means that the discharge should be subtracted by 1.8 to get the actual discharge. But remember, this graph is for 1 foot. So this graph is for 1 foot. So that's why the correction is 1. For 1 foot, the correction is 1. So that's why 1.8 is the answer. Now, what is the size of the flume that is given? That is 4 feet. The size of the flume that is given, 4 feet. So for 4 feet, this is 4 feet. What is the correction factor? The correction factor is 3.1. So it means we have to multiply this 3.1 with 1.8 to get the correction for 4 feet size flume. We have to apply this correction factor with 1.8, because this 1.8, this is for the 1 foot submergence. See here, 1 foot submerged partial flume. If you have a graph that is for 4 feet size, then you directly get this value. Clear? So that's why what we see here is that for 4 feet flume, for 4 feet flume, now Q correction, this is Q correction. That will be equal to 3.1, which is the correction factor for 4 feet size, into 1.8. So this will be equal to 5.58 CFS. 5.58 CFS. 3.1 into 1.8. 1.8 is here, and because this graph is for 1 foot, so for 4 feet size, the correction factor is 3.1. So 3.1 multiplied by 1.8, this is the correction for the 4 feet size flume. And now what will be the actual discharge? So the actual discharge will be then Q actual will be then equal to 67.92 minus 5.58. Because of submergence, the discharge is reduced. Clear? So minus 5.58. So this will be equal to 62.34 CFS. This is the answer. Cubic foot per second. This is the answer. So if there was no submergence, then we have free flow discharge, and 67.92 will be the answer. But because we have submergence, so we calculate this correction, and then this has to be subtracted from this formula, because these formulas are developed for free flow. So you subtract from here, and this is how we calculate the actual discharge.